Hello, in this video we will go over complex eigenvalues and eigenvectors. So this is still linear algebra complex eigenvalues. So what is a complex eigenvector? The eigenvalues of a matrix can be real or imaginary, hence we are forced to consider complex eigenvectors and complex eigenspaces. If the characteristic equation, let me scroll down. If the characteristic equation of a real matrix A has complex roots, then these roots provided critical information about A. If A is real, its complex eigenvalues come in conjugate pairs. So if A is real, its complex eigenvalues come in conjugate pairs. So let's look at an example. Example says, find the eigenvalues for the matrix, this 2 by 2 matrix, A, negative 2, 5, negative 1, 2. So how do you find the eigenvalues? So I've done this before. We've probably done this in the previous lecture. But so basically, you take the determinant of A minus lambda I equals to 0, right? And then so it's basically the determinant, and then it's these center ones. It's going to be negative 2 minus lambda. These ones stay the same, so negative 1 stays the same, and 5 stays the same. And then so you're basically your diagonals, and then 2 becomes 2 minus lambda, right? So what we do next is we take the determinant. How do you take the determinant of a 2 by 2? It's pretty simple. You take the major minus minor, right? So it's basically this whole thing times this minus negative 1 times 5, right? So that would be expressed as negative 2 minus lambda times 2 minus lambda minus bracket negative 1 times 5 equals 0. So if I FOIL this out, I'm going to get negative 2 times 2 is negative. So if I FOIL this out, this is what you're going to get. I'm going to save you work. You're going to get negative 4 plus 2 lambda minus 2 lambda plus lambda square plus 5. And when you simplify this, it's going to give you lambda square plus 1 equals to 0. And then go ahead and solve for lambda. So you're going to subtract 1. You get lambda squared equals to negative 1. And this is different from the other ones. When you solve for lambda and you take the square root, what happens? You're going to get imaginary, right? Remember, you can never have a negative in the radical, so that's going to be um I, and then it's really plus or minus square root of 1, which is basically 1. So your lambda is going to be plus or minus I. Okay? So you could say it like that, or you could say lambda equals I, or lambda equals negative I. Okay, not too bad, right? So let's do another example. So in this example, find the eigenvalues and eigenvectors for this 2 by 2 matrix, 5, 1, negative 2, 3. So it's still 2 by 2, which is, it's good, right? You know how to take it. It's easy to take it. So it's going to be the determinant. And then the diagonals are 5 and 3. So it's going to be 5 minus lambda. And then it's going to be 3 minus lambda. And then you have this 1 and negative 2. Okay, so equals to 0. And what you would do next is basically take the determinant of a 2 by 2, so it's major minus minor. So it's this subtracted by this. So that's going to give you 5 minus lambda times 3 minus lambda minus, and then it's negative 2 times 1 equals 0. And when you do the algebra, you get 15 minus 5 lambda minus 3 lambda plus lambda squared plus 2 equals 0. And then you put it all together, you get lambda minus 8 lambda plus 17 equals 0. And unfortunately, it doesn't factor out nicely. So what do you have to do? Yes, you have to do the quadratic formula. So my A is 1, B is negative 8, and C is 17. So our lambda is opposite of B, which is 8 plus or minus root B squared, which is 64 minus 4 times AC all over 2A. Okay, when you do the work, you get 8 plus you can put this all in the calculator and you get minus 4 all over 2. And when you simplify this, so as you can see, you can't have a negative in the radical, so you get an I. So when you simplify this, it's going to be lambda equals 8 plus or minus 2i all over 2. And when you simplify this, you're going to get lambda equals to 4 plus I, or lambda equals 4 minus I. Okay, so that's that one. Okay, what happens? Okay, so wait, that's in our, there's a two-part, right? We found the determinant. Now we have to find the eigenvectors. So this is where you have to like augment it with 0, right? So yeah. So remember we have two lambdas, 4 plus I and 4 minus I. So this is going to be the second part. Okay, so the second part is we're going to find x equals, basically it's this, a minus lambda I augmented with 0. So you set it up like this. Diagonals is 5 minus lambda. This is 1. This is negative 2. And then this is 3 minus lambda, right? Now, let's plug in lambda when lambda equals to 4 plus I. That's going to give you this. So what you see this? You just replace lambda with 4 plus I. And you get 5 minus 4 plus I. This is negative 2 augmented with 0. And then this is going to be 1. And it's 3 minus lambda, which is 4 plus I. Augmented with 0. So when you row, so when you try to row reduce, this is what you're gonna get. You're gonna get 1, 0, negative 1 minus I, and then this is 0. This augment, this is still 0. So recall this is column 1. This is x subscript 1. This is x subscript 2. So you get uh x1 equals to, hold on. So if you really, this is like saying 1x1 uh plus negative 1 minus I x subscript 2 equals 0. And then when you solve for x1, this is what you're going to get. X1 equals to negative parentheses negative 1 minus I x2. And then x2 is going to be x subscript 2 is 2, x2. So you're going to get your matrix is 1 plus I and 1. Yeah. Now we got to do this because remember we had two lambdas, so my second lambda was 4 minus I. So we have to do the same process for 4 minus I. Okay, so when you do that, you get this 5 minus 4 minus I. This is 1, and then this is negative 2. This is 3 minus 4 minus I augmented with 0, 0. And when you row reduce, because I'm going to save you time, you get this 1, 0, negative 1 plus I, 0, augmented 0, 0. And then this is x1, x2, right? So if you recall, this is 1 x1 plus negative 1 plus I x2 is 0. And when you solve for x1, you get minus negative 1 plus I x2. And then x2 is x2. And you get this vertice, 1 minus I 1. Okay, so your final answer for your eigenspace is those two matrices. So it's your eigenspace is going to be this. The first matrix was 1 plus I 1, and then the other matrix is this 1 minus I 1. Okay, okay, let's move on. So real and imaginary parts of vectors. The secret to rotation is hidden in the parts of a complex eigenvector. So here you have this little diagram. Um, so if you look at go ahead and draw the diagram and let's go over the theorem. Yeah, so the theorem says let A be a real 2 by 2 matrix with complex eigenvalues of A plus BI, an associated eigenvector in Rn, then A equals P times C times P inverse, and P is equal to the rel of vector V of IMV, and C equals this 2 by 2 matrix AB, negative B, A. So go ahead and copy that down. We'll go over one example of this, and then C equals P inverse times A times P, right? Yeah, so let's go ahead and copy that down. If you need to pause it, that's fine. Let's do one last example. So this last example states, let A equals this 2 by 2 matrix, 0 0.5, 0 0.75, minus 0 0.6, 1.1, and lambda equals to 0 0.8 minus 0 0.6 I. And vector V is this matrix, negative 2, negative 4, I5. Find P and C. So the question says find P and C. Whoops. So how do we do that? So step one, I'm going to set it up like this. So step one, P is going to equal to the rel of V of 1 M vector V. So this means this is the real C component. I mean, this is the real component of the vector. And then this is the imaginary component of the vector. So this IMV just means imaginary component of vector. Okay. So the real component was so let's do that. So the real is this one. So our real is going to be -2, 5, and then plus the imaginary -4 I plus 0 I. Right, this is your real, the REL, the REL vector, and then this is -4 I and 0 I is the imaginary. So that means your P is going to be -2, 5, -4, and 0, right? For step 2, now we're going to find C. So we got to find P and C. So we found P, which is this matrix, and now let's find C. So step 2. So find C is equal to P inverse times A times P. So it's basically this. 1 over the determinant of D minus C minus B A times it by A times P. Um, so how do you so 1 over what is the determinant of this? It's just basically major minus minus, so 0 times -2 is 0. Minus -4 times 5 is -20, which gives you +20, right? So 1 over determinant is 1 over 20. We just found that out. And then our D is 0. So it's basically I think you just flip these, right? And then you make the 5 and the -4 negative. Yes. So flip these. This is going to be 0. This is going to be -2. And then make the 5 and then -4 negative. So this is going to be -5. This is going to be +4. And then what did I do? So next is we found our A, and then our P is wait, actually 1/20 times this matrix is your P inverse. Okay? And then A is I think that was given, right? Yes, A was given. It was 0.5, 0.75, -0.6, and 1.1. And then my P was this one. That is -2, 5, -4, 0. So this is P inverse. This is going to be A, and then this is going to be P. So when you do, you could just put that in the calculator and you get your C. So your C is going to be this final answer. 0.8, 0.6, -0.6, 0.8. Okay, that is your final answer. Okay, we're gonna stop here, and this was pretty much a short video. The next video should be about inner product length. It's still linear algebra, and it's gonna be inner product length and orthogonality. Say ortho ortho orthogonality. Orthogonality. Okay, I'm gonna stop here.